Hello and welcome to an overview of Stable Diffusion. This is an incredible open source AI platform that we're going to dive into in deep detail as we go through this video. However, we're going to start right away by taking a look at some of the outputs from this incredible open source AI, and we're going to take a look at how you can easily and quickly get your hands dirty and go ahead and make some of these images yourself through various different means. And as always, this is all bookmarked, so you can jump ahead as you see fit. With that said, let's dive in. So it's just really cool that you can just go from, from this beta, and Hugging Face has this really nice interface where you can just go generate images really fast. They do have advanced options that you can select. If you really want performance, they even recommend that you go to the Dream Studio beta, and eventually they will have an API, but you can just log in with a Google account, for example, or just create an account with them, and then you can come here and modify your settings. I've generally kept the width and the height the same, and really tried to keep a lot of these steps pretty much where they have them set. You can see that you use up credits whenever you change these. So you'll just want to be aware of how many credits you're using per image. And then, so you can choose the number of samples that you generate as well. And if you run out of credits like I did, then you can purchase a membership for a really low cost by going to membership. And then you can purchase a membership. So you pay £10 basically per 1,000 generations. And so you can see, I can download my images. And what's really cool whenever you use their UI, I don't know if you can see this. Let me drag the image up, but it actually puts into the file name itself the actual query. So that's pretty cool too. If you do a lot of these like I have, that's actually really, really helpful, even though it's just a minor quality of life improvement. So we could say something, a dream of, I'm going to say Darth Vader riding a unicorn, and let's see what we get. That's hilarious. Oh man. So you can kind of play around with these, and sometimes it kind of gets stuck whenever you do one. Okay, that's really interesting. Yeah, that's not the best, but let's give it another go here. It's just really fun. Okay, that is hilarious. So it looks like it gave Darth Vader like a pointy little thing like the unicorn. But isn't that just so funny and interesting? And the fact that it's able to take that text, and basically what it's doing again is it's denoising essentially based on what it learned. So it's turning this into a really simple image, and then it's denoising that, which is just so interesting that it gets this kind of result that's so accurate. So anyway, really, really cool. I'll do one more here. Once again, it's kind of varying off of that one. I don't know that this tool lets you use an existing image. It does let you see your history, and it also gives you a prompt guide, which is really, really helpful. So it talks about how to prompt the system, which I highly recommend reading no matter where you're using this, even if it's locally. This prompt guide is really critical. So take a look at this and make sure you understand some of these concepts, because they definitely matter. You can also sort of tell it the different rendering. So definitely take a look at that. There's also an FAQ area, social, etc. And you can see your history of what you've had it generate as well. So really, really cool. Let me know if you're interested in seeing some projects where we use the API, or where we sort of like go into the weeds on setting up your local machine with this. And with that said, let me go over to our Google Colab and show you that setup. Okay, so this is a copy from the AssemblyAI team, who did an awesome job producing a video and going into the detailed weeds of how Stable Diffusion works, and then also making this available. So I've included a link to them. That is an incredible YouTube channel and website to follow. So kudos to them for what they've done. And so I just made a copy of that, followed their steps. And essentially what you do is you basically you do have to purchase the pro version for this to run effectively. But you can clone their Colab, or you can clone this one. What I've done is I've extended what they made and made it so that it also will allow you to upload images and use those images to upsample them or reduce the noise from them, which I think is a lot of fun and pretty interesting. But yeah, so you just go through and you complete these steps, and I'm going to let these run in the background, but I'll make it go really fast for you. And I'll just complete this so you can see that everything runs and what the outputs are here. And just to interrupt briefly here, I just want to say the really cool thing about this is anyone can do this. You don't have to have technical knowledge. I literally just copied this file, and you can see very clearly what's happening. And basically you're just pressing these little play buttons. You don't have to have a lot of advanced technical knowledge to make your own clone of the repo, get it downloaded, and have it actually work. And you get to have your own private repo, essentially, where you are playing around with Stable Diffusion yourself in the cloud. Again, no technical knowledge necessary. So this is really how a lot of AI interaction will probably work going forward, and really is working for a lot of the bigger models, because it's just not possible in most cases for people to download them and play with them and tweak them and do research locally, because they're so large and they require so much RAM and GPU, etc. But anyway, I'll let this finish and then we'll show some demonstration of it. Okay, so now that that's done, now we have our environment, and we can literally run a image and create an image. And I'm doing 4 up at a time. And I upgraded to the Pro Plus during this video just so things would go a little bit faster. But I've run everything on the Pro level, which was $10 a month or $9.99 a month, which is really, really cool and not very expensive. So the first time that this runs, it downloads a lot of packages. And then once it stays in memory on the Colab environment, then it doesn't have to re-download or do all of the subsequent or the precursor steps that you've seen. And then we can just run these over and over again. So you can see it's having to download a good amount of stuff. The throughput is pretty high here though. Okay, so now we're actually running this through the model. Now, once this runs and finishes, I'm going to download the best of the 4 images, and then I'm going to upsample it or denoise it even more, and use that as sort of a starting place to then iterate off of. And here you can see, in case I didn't make it clear, my prompt was a photograph of a raccoon astronaut flying on a friendly space dragon, hyperreal, intricate, sharp focus. And I have 4 samples that I'm using, and I did 100 DDIM steps. Okay, so it's finished, and now we can see our images are in this samples folder. And you can just double click on them and they will open to the right. So that's pretty cute. That's pretty awesome. Okay, it's kind of artistic. That one's a little more like 1970s feel. Oh my gosh, this is hilarious. Look at that. Okay, so this is the one I'm going to use. So let me download that, and I'm going to make a folder. And you can see I added this section. I'm just going to make a folder here called Uploads within the Stable Diffusion folder. So there's my uploads, and then I'm going to drag in my upload. And it's just letting me know that it's going to remove this once this instance is destroyed, which will happen at some point. It's not a persistent image or instance. Okay, so I'm just going to label this starter.png, and then we'll change this to starter. Okay, so now I'm going to get my text as well, because I've got different text there. Copy that down. All right. And so I could change this if I want and sort of morph it, but I'm just going to use it to sort of upscale this, but we'll let it run with the 4. All right, so let's go check our samples. Just going to refresh this folder. Oh my gosh, that is so awesome. Wow, that's pretty cool too. Wow, that is crazy looking. Oh wow, that's pretty cool too. Look at that, unreal. Oh, okay, definitely not my favorite, but these are so cool. Look at these. That is literally ridiculous. And awesome. Okay, so whenever we dive into the actual code for Stable Diffusion, the really cool thing that you'll see is all of it is literally open source. So we have access to literally everything. Now, if you sort of think about this from a high level, the bottom line is that you can take this and do a lot with it yourself to play around and experiment. But the other thing that you can do from this is you can sort of understand when you are experimenting, even if you're using the Stable Diffusion that's available in a cloud environment or etc. Just by understanding some of the parameters better and how it's programmed, this will help you to sort of get into the weeds about how the outputs work. And I'll go into some detailed examples by reviewing the code later on. But to start with, I wanted to quickly take a look at some high-level points from the GitHub repo. And the first thing you can see here is they do go into some information, some detail about some of the example pictures that were generated. And I'm just going to zoom in so you can sort of take a look at these. These are really incredible. And one of the things that I think is really helpful is they also go into links and link out to some of their previous work. And this is particularly helpful because this will allow you to sort of see how this all came together. And it really gives you the backing information if you want to get into a lot of detail. Why, here it is. You can literally drill down into the detail that you're going to need to understand the nuances of how this physically works. Now, again, I'll go into a lot more of that later on. But one of the biggest things that I would say in general is that this model is pretty interesting about it is it's using a latent text to image diffusion model. So effectively what they're doing is they're taking this text that a user inputs and then turning that into an image. And then that image is used to do the diffusion on. And so the diffusion in general terms is basically adding a bunch of noise and then denoising and training a AI on this, a certain number of times. And we'll have or will go into how many times this particular set of training has gone through. And there are different versions. So if you look at the version 1-1 through 1-4, you can see the different details of the results and the versions. But ultimately, the big thing here is that one of the things that it does is it basically denoises the images. So conceptually, it's able to just add really like upscale images from something really simple. And that's really the context that we're working in. So if we're taking text and turning it to a really simple image, that's sort of a separate step. And then really the diffusion is where we're going from this sort of simple image and then we're completing this diffusion step and we are turning it into this really upscaled, precise image. However, of course, if you're starting from a simple image, it's not going to literally be physically possible to precisely control the output. And so that's sort of one of the base limitations, but it doesn't mean that the outputs are not going to be almost eerily real and, of course, very creative and interesting, as you can see from some of them that I have showing on the screen. One of the other things that I'll point out about the Stable Diffusion training in particular, and you can see that here, they were able to train a latent diffusion model on 512 by 512 images. So they basically trained it on this LAION 5B database. And this database, they used a subset of 512 by 512 images. I noticed whenever I was testing this, if I used different size images, and this is probably mostly just a user issue as opposed to anything else. But I did notice that my ability to get the same level of results was reduced. The other thing that I'll point out is it does use a substantial amount of resources. It's sort of an exponential increase. It's at least a non-linear increase in resources as you go about increasing the image size, which makes sense in general. So anyway, 512 by 512 seems to work quite well. And that does make sense since that's what all of the training was done on. So in theory, you could take this system and train it on a different type of image. And instead of training it on this database, you could train it on different images that are applicable to your scenario. And here's the thing, you can actually access all of this and do this type of work yourself if you want, which is really helpful if you think about it, because one of the things that I noticed in my testing, again, was that basically this system has some biases toward the images that it was trained on. That literally makes sense if you think about the mechanics of it. It's not going to be able to interpolate stuff that it literally has never seen before or has very small data sets for. So anyway, all of that said, we'll just keep going and digging in. And basically, one of the things that it talks about here is that this particular platform, Stable Diffusion, is similar to Google's Imagen. It uses a frozen clip VIT L14 text encoder to condition the model on text prompts. And then it uses an 860 million UNet and 123 million text encoder. And the model is relatively lightweight and runs on a GPU with at least 10 gigs of VRAM. So again, this is the really cool part, is because it's set up this way, it can be run in a local environment. Not a beefy machine necessarily. So you can literally download it and run it in your local environment. And again, in this video, we have a section that goes over exactly how to do that. Now, the other thing is, if you take a look at the model card, which I always think is interesting to do, you can dig into the actual model card itself. Okay, so in order to then access the model card, what I did was I literally clicked the model card link, went to the diffusers library, and I chose V1-4, and then I have to share my information. So this is really important if you're using this or wanting to use this for a certain scenario that doesn't really fall into line. You do need to read this documentation and make sure you're comfortable with it. So anyway, you can then access the repo, go through and read some of the details around the model card for this particular instance. So we'll just zoom right in. First of all, this was developed by Robin Rombach and Patrick Esser. The model type, diffusion-based text-to-image generation model. It's English for now, at least. And it uses the Creative ML OpenRail M license. Now, if you haven't seen this, we'll just quickly take a look at this so you have access to it visually. But you can see that this goes into some detail about basically what the goals are behind this. And essentially, they're saying that each effective use of this can be released under different licensing terms, but they always have to include at minimum the same use-based restrictions as the one in the original license. So essentially what they're saying is you have to at least be as restrictive as they are with the use of this system. The other thing is, and you can go through and read the detailed terms, but the other thing is that they also are saying that there is a watermark that's built in, that's a non-visible, sort of invisible to the human eye watermark. And this will allow anyone who's scanning sort of like an internet site, for example, or any kind of resource, they'll be able to detect that watermark if they are looking for it, which is pretty helpful, obviously. So basically, they go into detail around the conditions of use, distribution, and redistribution. And again, if you're planning on using this, you do want to make sure you understand, and in particular, the use-based restrictions. And they're set forth in Attachment A. So this is sort of like a standard set of legal documents for the open source licensing. And then these are the use restrictions. So obviously, they don't want you to violate any laws. Can't be used to exploit minors, etc., disseminate false information, personally identifiable information, defame, disparage, or otherwise harass, And then for fully automated decision making, basically legal rights, that kind of thing, like being able to make a pre-assessment that just would be based on a poorly trained AI effectively, without saying it hopefully too crass, but I mean, that's the reality. For making a legal decision, you need a lot of information. For any use intended to or which has the effect of discriminating, to exploit any of the vulnerabilities of a specific group, for any use intended to or which has the effect of discriminating, to provide medical advice, to generate or disseminate information, the purpose to be used for administration of justice or law enforcement, and then that's it. So it is pretty open in general with the terms. So again, you can dig in and literally read the legal terms yourself and get into those and understand what they are. But they are pretty open in general. Then they go into a description of the model, the latent diffusion model. And this is a really, really nice set of overview if you take a look at this Imagen paper. Okay, so in this paper, you can see the abstract, and basically the summary is a text-to-image diffusion model with an unprecedented degree of photorealism and a deep level of language understanding. It builds on the power of large transformer language models in understanding text and hinges on the strength of diffusion models in high-fidelity image generation. So these are sort of two separate thought processes here. The large transformer language models, and then the diffusion models for text and image generation, respectively. The key discovery is that generic large language models pre-trained on text-only corpora are surprisingly effective at encoding text for image synthesis. Increasing the size of the language model in Imagen boosts both sample fidelity and image text alignment much more than increasing the size of the image diffusion model. So basically they're saying this text side of things is a surprising opportunity for optimization. The better and more accurate sort of your starting place is, the better it's going to be for the diffusion model that is then taking that input and generating an output. Imagen achieves a new state-of-the-art FID score of 7.27 on the COCO dataset without ever training on COCO. And human raters find Imagen samples to be on par with COCO data itself in image text alignment. To assess text-to-image models in greater depth, we introduced Drawbench, a comprehensive and challenging benchmark for text-to-image models. With Drawbench, we compare Imagen with recent methods including VQGAN Clip, latent diffusion models, Glide, and DALL-E 2, and find that human raters prefer Imagen over other models in side-by-side comparisons. And so basically, they then go into detail about how it works. And we've talked about Imagen before in some of our previous videos. But this text encoder piece is one of the biggest areas of opportunity. And I think fundamentally, a lot of the researchers were sort of surprised by this. And you can sense that in the tone in the abstract too. But basically, the text encoder was sort of a big opportunity for major improvement. And then, of course, the diffusion model is what we're using on the actual image generation itself. So anyway, I think that this is really helpful. I won't go into all of the detail on this. Just suffice to say that it's really helpful to be able to reference this, and then sort of get into, this whole idea of what the latent diffusion models are and how they work. And you don't necessarily need to go into all of the weeds on all of these and literally understand everything. Of course, I think it's not necessarily bad, but you don't have to go into detail and understand literally everything. It just can be helpful to know sort of where to keep digging if you need to get more fidelity and understand what's causing the outputs that you're seeing, so you can adjust those and have control over them. Okay, so you can see in this particular paper, this was co-authored with Robin Rombach and Patrick Esser. So you can sort of see the consistency here between this paper, the authors, and the CompViz Stable Diffusion platform. And bottom line, if you sort of get into the weeds on this, there are some incredibly helpful images that they have if you want to just quickly get a good idea of what's going on. You can even see they give sort of example comparisons of the level of detail. So they're sort of saying, this is the input here is the output that comes back and the level of detail. So you've got DALL-E, their Stable Diffusion platform, or in this particular paper, this specific latent diffusion model, and then this VQGAN. And you can sort of see the difference in the outputs versus the input. And the idea here is that we're adding noise and then we're denoising. And this is sort of something that the AI community has figured out works to generate images after you complete training like this. So if you go further into the paper, they have a really nice sort of visual of how the actual process works. So this is a really nice image that you can see from this paper about latent diffusion. And without going into all of the detail on exactly how this works, I'll just make a note that if you're interested, I'm more than happy to decompose each of the steps in this and really just go through exactly how this is mechanically working. And even go through some examples physically. If folks are interested, just leave a comment and I'll be happy to make a video about that as well. I would love to do it. I just want to make sure there's interest for it. But anyway, the main thing that you get from this is you can drill down and understand some of the nuance and differences between the different systems. And this is a really helpful set of information to be able to base sort of how you're taking advantage of and working with this Stable Diffusion platform. And then you can also see here, whenever we're continuing on this, the data card, the model, they actually go into some examples about how to use it. And they even go into examples about how to sort of limit, if you are limited by GPU memory and have less than 10 gigs of GPU RAM, please make sure to load the Stable Diffusion pipeline in float 16 precision instead of the default float 32. You can also do so by telling diffusers to expect the weights to be in float 16 precision. So that's pretty cool. So they're showing you where you can set it to float 16, which, you know, I think just shows how serious this group is about trying to let more people use it and get their hands on it so they can experiment and learn. And so anyway, they talk about the uses and they go into how the model is intended for research only. So literally that is the intention. Possible research areas and tasks include safe deployment of models, which have the potential to generate harmful content, probing and understanding the limitations and biases of generative models, generation of artworks and use in design and other artistic processes, applications in educational or creative tools, and research on generative models. Excluded uses are described below. So misuse, malicious use, and out-of-scope use. This is taken from the DALL-E mini model card, but applies in the same way to Stable Diffusion. It should not be used to create or disseminate images that create hostile or alienating environments for other people and that would foreseeably people would find disturbing, distressing, or offensive, or that propagates historical or current stereotypes. Out of use scope was not trained to be factual or true representation of people or events, and therefore using the model to generate such content is out of scope for the abilities of this model. Misuse and malicious use. Using this model to generate content that is cruel to individuals is a misuse of this model. This includes, but is not limited to, and you can read all of the different scenarios here. One of the things that I'll note is that they will literally put a Rickroll image into the text or into the image output if it appears that it's violating these terms, the result that gets generated. So if you actually look at the code, which we have access to, there's literally a line in the code where it adds the Rickroll image to replace the image that it generated. It also appears to blur out the image as an alternative in the actual Stable Diffusion website example on their public site. So that's pretty interesting. They also go into the limitations and bias. So one of the things that they note is that it does not achieve perfect photorealism. It cannot render legible text. It does not perform well on more difficult tasks which involve compositionally, such as rendering an image corresponding to a red cube on top of a blue sphere. So it really is leveraging information that it sort of is already trained on, and then just sort of casting those sets of trained information elsewhere. And it really has trouble with this compositionality, not compositionally, but compositionality. Faces and people in general are not particularly generated well. It was trained mainly with English captions and won't necessarily work well in other languages. The auto-encoding part of the model is lossy. The model was trained on a large-scale data set, which contains adult material and is not fit for product use without additional safety mechanisms and considerations. No additional measures were used to duplicate the data set. As a result, they observe some degree of memorization for images that are duplicated in the training data. The training data can be searched here to possibly assist in the detection of memorized images. So you can actually go and search and see if there are duplicates. Definitely, I would say it does tend to have a pretty strong bias, and you can see it talks about the bias. While the capabilities of the image generation models are impressive, they can also reinforce or exacerbate social biases. Stable Diffusion version 1 was trained on subsets of LAION 2B, which consists of images that are primarily limited to English descriptions. Text and images from communities and cultures that use other languages are likely to be insufficiently accounted for. This affects the overall output of the model, as white and Western cultures are often set as the default. Further, the ability of the model to generate content with non-English prompts is significantly worse than with English prompts. So they should team up with Bloom so that they can fix that. Training data. The model developers use the following data sets for training the model. LAION 2B and subsets thereof. The training procedure. Stable Diffusion V14 is a latent diffusion model, which combines an autoencoder with a diffusion model that is trained in the latent space of the autoencoder. During training, images are encoded through an encoder, which turns images into latent representations. The autoencoder uses a relative downsampling factor of 8 and maps images of shape height by width by 3 to latents of shape height over f by width over f by 4. If you're not familiar with downsampling, basically the idea is that we're taking a representative pixel out of a group of pixels, and we're simply replacing that group of pixels with just the one representative pixel. So we're basically getting rid of data and sort of like picking one piece of that data that we're going to keep. So if you had a picture with 100 by 100 pixels and you downsampled by 10, then you would, with every 10 pixel group, you would just take one representative pixel. And there are, of course, different ways you can sort of select which pixel you would take. Would you take the brightest pixel or the darkest pixel, or would you take the medium pixel, or would you collectively determine the weighting of all the pixels and then average it out? These are sort of some of the nuances that I don't see here, but obviously we can get into. Text prompts are encoded through a VITL/14 text encoder. The non-pulled output of the text encoder is fed into the UNet backbone of the latent diffusion model via cross attention. If you're not familiar with attention, basically the concept of attention is that you have so much data. If you try to process all of this and literally give it all the same attention when you're processing it, it's not going to be effective. So you literally, through different algorithms or logic, determine a focus of the attention of the model, and you basically eliminate noise within the image. Human beings, we do this constantly. Whenever we're looking at something, we tend to allow whatever else we're not focused on and we're not giving our attention to sort of just not be a part of our processing. It's just really our major focus goes to whatever we're giving our attention to, and then we sort of give our attention back and just sort of like fill in the gaps. If you do any research on human vision, you'll see that's basically what happens. We don't process a lot of the information. That's why magic tricks work so well, is because we're just not processing things we're not focusing on. So that's exactly what we're taking advantage of here with this cross attention. And then the whole cross attention piece is sort of a more sophisticated way of letting this sort of attention to multiple things sort of backfill into itself intelligently. The loss is a reconstruction objective between the noise that was added to the latent and the prediction made by the UNet. And then we currently provide 4 checkpoints, which were trained as follows. And this is really cool because you can actually go in and look at the checkpoints and the FID results that occurred on those different checkpoints. And this is really powerful because you can understand exactly what the performance was at each of these checkpoints. And then again, sort of the idea here would be, depending on how detailed you want to get, you could actually recreate this process for your specific data set, which I think is so cool. So anyway, you can see the hardware that was used. There were 32 by 8 A100 GPUs. The app optimizer was Atom W. There were 2 gradient accumulations. The batch was 2048, and the learning rate was a warm up to 0.0001 for 10,000 steps, and then kept constant. Okay, and so here are the evaluation results. If you look at the FID scores, FID versus clip scores, and basically you can see that as we go through the versions, this gets better and better. And version 1.4 is pretty close to this green line from version 1.3. And this again is the 512 by 512 samples. So it's evaluated using 50 PLMS steps and 10,000 random prompts from the COCO 2017 validation set. And you'll see a lot of reference to this COCO data set, which basically these systems, these image systems, are not pre-trained on. And then they go, after the system is trained, they go evaluate these COCO 2017 or other COCO data sets, and then compare to each other on that benchmark. Then they talk about the environmental impact based on the usage. And there are also citations here as well. Well, hey guys, I hope you enjoyed watching this edition of Tech Launch. Thanks for watching as always. If you'd like to see more of these, feel free to smash the like and hit subscribe, and we'll see you in the next one. Thanks again, and bye for now.